Let's talk about time. Have you ever wondered how time is measured and how to determine the world's time zone? The scientists take advantage of physical clocks to measure the time. A physical clock is actually a physical process calculated by a specific method. One example of it is the Earth's rotation, calculated in solar days. Physical clocks are mostly work in cyclical manners. The determination of the world's time zone requires one or more physical clocks. Every concrete time is a measurement of some physical clock. For instance, a wind-up watch provides the time now by measuring the rate at which a coiled, wound spring unwinds. A physical clock always has its limitations. Some are run by batteries, some can be wound up, some by sand, some by sun, and some by water. In the International System of Units, SI, the unit of time is second. But what really is a second, and how is it calculated? 1 second is the time that elapses during 9,192,631,770 cycles of the radiation produced by the transition between two levels of the cesium-133 atom. This is determined by an atomic clock, also known as a radio clock. Heard of that before? Let's first take a look at a pendulum clock. A pendulum clock tells time using a pendulum, a swinging weight that provides a harmonic oscillation by swinging back and forth in a precise time interval, dependent on its length. The same principle is what the atomic clock is based on, but of course with a significantly better accuracy, due to the much higher frequency and stability of oscillation of atom. All the different types of atomic clocks commonly share the same working principle. Initially, the atoms are heated in an oven prior to their bundling into a beam. There are two possible energy states or hyperfine levels in each atom, namely state A and B. In this step, atoms in state B are eliminated by a magnetic field, while atoms in state A remain in the beam. In the second step, the state A atoms are exposed to microwave radiation by sending them through a resonator. Due to this radiation, some of the state A atoms are shifting to state B. A second magnetic field is then fired to eliminate atoms that are still in state A. The remaining shifted state B atoms are then counted using a detector. The frequency of the microwave radiation determines how many of state A atoms that can be shifted to state B atoms. The more synchronization events happen between the frequency of microwave radiation with the inherent frequency of oscillation of the state A atoms, the more atoms can be shifted into state B atoms. In fact, the purpose of this step is to adjust the microwave radiation frequency to match the frequency of oscillation of the atoms. In the 9,192,631,770th oscillation of the atoms, it is defined as 1 second. The mouthful number of oscillations gives us an idea of how accurate the atomic clock is. Atomic clocks are so accurate that they are known to make a 1 second error in about, can you guess? If you guessed 100 or 200,000 years, that is incorrect. The clock is known to make a 1 second error in about 10 million years. So how many of this atomic clock exist worldwide? Quite a lot, actually. So far, there are 400 of these clocks worldwide, owned by around 70 meteorological institutions and observatories, and are used to determine Coordinated Universal Time, or more famously known as the UTC, and local times around the world. What's even more interesting is that the ultra-precise Mercury Ion Atomic Clock, or known as Deep Space Atomic Clock, DSAC, is now operational and is ready to improve the accuracy of satellite signaling. A second can also be defined by the propagation of electromagnetic field. 1 second is a time needed to propagate an electromagnetic field within a vacuum to cover a distance of 299,792,458 meters, or around 300,000 kilometers. We also know that a mean solar day is 24 hours with 60 minutes per hour and 60 seconds per minute. Multiplied together equals to 86,400 seconds. This means 1 second is equal to 1/86,400th solar day. The accuracy of the definition is, however, affected by the irregularities of the Earth's orbit around the Sun, which causing some solar days to be longer than 24 hours, while some others are shorter.